In this video, we are going to discuss techniques for analyzing slightly more complex circuits involving resistors in series and parallel combined. Now, our goal is to find the voltage across, the current through, and the power output of each of these resistors. Now, the new concept that we haven't seen before is power output. The equation for this is simply that the power is equal to the current through the resistor multiplied by the voltage across a given resistor. And the simple way to think of why this should be the equation that we use is that the current is the charge per second, coulombs per second. The voltage is the joules per coulomb. The coulombs cancel out and we get joules per second, which is the equation of power, right? How much energy do we get per coulomb? How many coulombs do we have per second? Energy per second is our unit for power. Now, in order to analyze this circuit, our goal is going to be to combine the resistors using our equivalent resistance for parallel and series resistors in order to get a resistor that looks like the equivalent resistance of all of our resistors combined. So our goal is to be able to write this complex circuit as a simple circuit with one battery and one resistor. Once we are at this point, we'll know a voltage and an equivalent resistance, which means that we can find out the current through this resistor. And once we do that, we're going to be able to build our way back up using that known current to find out the current and voltage for each of these resistors, along with the power. Now let's look explicitly at how we can begin to combine these resistors to find the total resistance. So first, what we need to know is, what are we actually looking for? Well, the most handy definitions that I have for series and parallel are that in parallel, the two sides of any resistors in parallel are connected by a perfect conductor. This also means that the two resistors will have the same voltage drop across them because for example, these two resistors have the same voltage drop across them. How do I know? Because the two sides of each of the resistors is connected by a conductor. So the right sides are connected by a conductor. And remember, our third fake Kirchhoff law is that any two locations connected by a conductor are at the same voltage. So the right side of these two resistors is at the same voltage. The left side is also at the same voltage because they are connected by a conductor. And so these two resistors must be in parallel. In fact, all three of these resistors together are in parallel because the right sides are all connected by a conductor and the left sides are all connected by a conductor. They all see the same potential drop, therefore, and are all in parallel. So, how can we use that knowledge that these three resistors are in parallel to simplify our circuit? Well, we can simply find the equivalent resistance using our parallel resistance equation. That is, that the resistance in parallel is 1 over R total is 1 over R1 plus 1 over R2, etc. So 1 over R234 is 1 over 20 ohms plus 1 over 10 ohms plus 1 over 2 ohms, and then that equals 1.54 ohms. Before we move on with the rest of our analysis, I just want to quickly note what you should be thinking about when you are first starting to look at a circuit like this. We already saw that these three resistors together are in parallel, but it is important to know kind of where to start on a circuit like this. So what you are going to look for is resistors where the two sides of the resistor are connected by a conductor, therefore they are at the same potential difference across the resistors, or resistors where there are no junctions between the two resistors. So, for example, it would be a bad idea to start with R1 and R2. I don't have a good way of combining these two resistors because there is a junction between them, and they are not, the two sides of the resistors are not connected by a conductor. So they are connected by a conductor on this side, but on the other side, in order to get from here to here from the other side of the resistor, we need to go through a resistor and a battery, not simply connected by a perfect conductor. So these two resistors are clearly not in parallel, right? The same thing for R1 and R3 and R1 and R4, etc. So in general, what you are going to be looking for whenever you look at a circuit like this is a discrete set of resistors that you can simplify in that moment. There may be multiple choices. For example, R1 and R5 are actually in series. How do I know? Because I can get from 5 to 1 without going through a junction. Likewise, I know that all of the current that flows through R5 goes through the battery and then through R1. And the resistors that are in series have the same current. All of the charge that flows through one of the resistors also flows through the other. So if you can prove that all of the current that flows through one of the resistors also flows through the other and vice versa, that is, everything that goes through R5 also goes through R1 and vice versa, that tells you that those two resistors are in series, which is true for these two. That is clearly not true for R1 and R2. So let's just disprove again that they're not in series. All of the current that flows through R1 distinctly does not flow through R2. Some of it goes to R3 and some of it goes to R4, again showing that these two resistors are not in series. So these are just a few different ways you can use of analyzing whether resistors are in series or parallel. Okay, now that we have that analysis, we can go back to our simplified circuit where we have taken our resistors 2, 3, and 4 and written their equivalent resistance. So we have replaced 3 resistors with effectively 1 in this diagram, and by doing so we have simplified the circuit and gotten closer to an equivalent resistance. All right, well now we clearly have 3 resistors in series with one another, right? I can get from each of the resistors to the next without passing through any junctions, and I can easily see that every electron that flows through R1 also flows through R2, 3, 4, and also flows through R5. So we have this simplified circuit, and now we can just use our series resistance rule, where we simply add up the resistance of each of the resistors in series to find the total resistance. So we find that the total resistance of this entire circuit, when we combine all of the resistors appropriately, is 7.54 ohms. Notice again that even though the largest resistors are 20 ohms and 10 ohms, those resistors show up in a parallel part of the circuit, and the sum of resistors in parallel is always smaller than the smallest resistance in parallel. So my smallest resistance in parallel here is 2 ohms, and my equivalent resistance is only 1.54 ohms for the R234, right? So the total resistance is certainly not simply the sum of all of the resistors. In fact, it turns out in this case to be smaller than the largest resistor in the circuit, because that resistor shows up in parallel with other smaller resistors like the 2 ohm resistor. Okay, now what we can do is we can take this simple circuit here and we can find the total current. And this is kind of what we were searching for from the beginning, because once we have the total current, we are going to be able to build our circuit back up to find all of the values that we're looking for, the currents and the voltages and the powers through each of these resistors. So this here is the total current that runs through the battery and therefore runs through all of the resistors combined. It's simply the voltage of the battery divided by the total resistance of all of them combined, which is 1.33 amps. Now that we have the total current, we can back off one step of the simplification and return to this picture here. Now what we know is we have 3 resistors in series with one another, and we know the current through each of those resistors. Why? Because we know the current through the battery, And every single one of these resistors is in series with the battery. It must have the same current as the battery. So we can therefore calculate the voltage across each of these resistors using Ohm's law. So V1 is going to be I1 times R1, which is the total current, because we are in series with the battery, times R1. We do the same thing for V2, 3, 4 together, and we do the same thing for V5. So we have now found the voltage across the combined voltage for 2, 3, 4, and the voltage across 5. Now, as a quick double check, what you can do is you can add up all of these voltages and realize that it should be 10 volts. This is due to the first Kirchhoff law that says the total change in voltage around a full loop should be 0. We gain 10 volts in the battery, which means that we should lose 10 volts for our circuit combined. And if you add these up, you will get something that is just over 10 volts. The reason that you don't get exactly 10 volts back is because we have rounded in each of these numbers here. And this makes our math a lot easier because we're not carrying around all of these algebraic terms in order to be exact. But when we rounded here, it means that all of our values are slightly off due to that rounding error. So if you add up all of these voltages, you will get a number that is slightly bigger than 10 volts. But that doesn't mean we're wrong, it just means that we had a rounding error. If you wanted to be super precise about it, you would have to keep all of these resistances and currents as ratios such that you didn't lose any decimal places. Now that we've gained all of the information that we can from our previous picture, it is time to go back and look at our original circuit. So at this point, we have found the voltage through resistor 1, the voltage through resistor 5, and the voltage through the resistor 2, 3, 4. Now, because these resistors are in parallel, they all feel the same voltage. And what we found in the previous drawing was the difference in voltage between here to the left of all of these resistors and here to the right of all of these resistors, which means that we found the voltage across all of these resistors individually. That is that the voltage 2, 3, 4 is actually equal to voltage 2, which is the same as voltage 3, which is the same as voltage 4. So that is 2.05 volts. Now what we can do is we can use the fact that we know the resistance of each of these and the voltage across each of these to find the current through 2, 3, and 4 using Ohm's law once again. So doing this using our known voltage along with the known resistance, we are able to calculate the current through each of these resistors individually. And now, if you look, we have our currents for each of the resistors, our voltages for each of the resistors, and we can then multiply those two things together, voltage times current, in order to find the power of these resistors. Notice that resistors with a higher current or a higher voltage tend to have higher power. So resistor 5 has a large voltage across it, and it gets the largest possible current through it. That is, it gets all of the battery current and it has the largest voltage. Therefore, it has a large power output. If we look at, for example, P4 here, our 20 ohm resistor, you might think, oh, that's a really big resistor, it's going to have a very large power output. But what we find is that because it is in parallel with the other resistors, it actually has a very low current. I4 is very small. Why? Because the current has to split between these three resistors, and the current will naturally go through the path of least resistance, which means you're going to get more current through the lower value resistors. So the 2 ohm resistor is going to have more current through it than the higher resistance resistors when they are in parallel. You won't get 0 through the 20 ohm resistor. You won't get 0 current, but you'll just get less, right? Because you have the same voltage, but more resistance. You have the same numerator, but a larger denominator, leading to a smaller current, and therefore a smaller power output. So our very high resistance resistor in parallel has a very low power output, not many watts associated with that resistor. So in general, what we have been able to do is that we have been able to break down our circuit by identifying resistors in series and parallel and finding equivalent resistance. We then found the total current through the battery and then rebuilt our circuit using the knowledge of that total current to find the voltage and current through the resistors individually. Once we had the current and voltage for each of the resistors, we then were able to simply multiply those values together to find the power output.